Welcome back, everyone. The topic for today actually is going to merge together two concepts we've used in this course quite a bit, the topic of limits and the topic of tangent lines that approximate the graph of a curved function or curved graph. And so this little theorem that we're going to learn today, called L'Hopital's rule, kind of ties together those topics. It's going to give us a way to solve limits that are in this indeterminate form that we've seen a number of times and have other ways to solve them. However, in some instances, the methods you use so far will not be good enough. And we learned this little theorem called L'Hopital's rule that will help in a number of situations. So to get us kind of ready to see how that theorem probably came about or was discovered, we're going to go back and look at those two topics, tangent lines and limits, one more time. So our little warm-up problem today is first a problem about tangent lines. I've got two functions here, and it turns out they both contain, the graphs both contain the point 1, 0. The first function is the natural logarithm function. I can easily confirm that f of 1 is, since it's the natural log of 1, will be 0. Similarly, I can easily confirm that this function g of x, when evaluated with 1, would be 1 squared plus 3 times 1 minus 4. That is also 0. What we're asked to do is write the equation of the tangent line to each graph at the point 1, 0. Well, the other ingredient for any line is to know the slope. And that's the main topic of differential calculus. The slope of a tangent line is found with a derivative. So the derivative of the logarithm function is 1 over x. And so the slope of the tangent line at the point 1, 0 will be the derivative evaluated at 1, which is going to be equal to 1, which makes now the equation of the tangent line in point slope form, y minus 0 equals the slope 1 times x minus 1. And in the previous lesson, we would have solved this for y and called it L of x as the linear approximation. And I'm going to write that as 0 plus 1 times x minus 1. You could also just simplify all of that and just call it x minus 1. But since we're going to do another one of these down here, I'm going to add a little subscript to this, the letter f, to say that is the linear approximation of f of x. And the linear approximation is x minus 1. And remember, what that means is the graph of the logarithm function essentially looks like this. Kind of bends around here. It does contain the point 1, 0. And the tangent line has a slope of 1, as we just discovered, so it kind of comes down like so. And so the idea here is this line is a good approximator of this curve as long as I am within a decent small little window around it. Okay. The curve and the line look a lot the same. So if I were to evaluate this linear function, just x minus 1, using a value of x that is reasonably close to 1, I get a pretty good estimate of the natural log of that number. So let's try it again here with number 2. I need to find the derivative. G prime of x is 2x plus 3, so the slope at x equals 1 is going to be 2 times 1 plus 3, so I'm going to get 5. And in point slope form means my line is y minus 0 equals slope 5 times x minus 1. So linear approximation of g, I am going to distribute out this. I'm just going to get 5x minus 5. Okay. Now, we want to tie in the topic of solving a limit today. So what if I were to build an expression by dividing the two functions that I have right here, and then solve the limit when x is approaching 1? Okay, well, notice we used 1 in the previous problem also, the x coordinate there. So now this is going to ask for the limit when x approaches 1 of the natural log of x over x squared plus 3x minus 4. And this immediately reminds me of some limits we solved in the previous units, where our first attempt should be to plug in the number like 1. But if I do that, I'm going to get this very common indeterminate form, 0 divided by 0. And what we learned many times this year is that does not give us the answer to the limit. It also doesn't tell us if the limit doesn't exist. It just says try something else. Now you could, and the problem here is suggesting we use a table or a graph to estimate the limit. So if you want to pause the video for a minute here, you could type this expression into your calculator and make it y1 equals, and use a table or a graph to estimate what is the graph doing, or what is the value of this whole expression doing when we get close to 1. You will see the limit does exist, but I'm going to leave it to you to try that with your calculator and see. You would want to put in numbers for x that are really close to 1, like 0.9 or 0.99, 1.01, 1.1, to get an idea of what is happening here. You'll see the limit does exist, but we're going to hold off now and try and show you an alternate way to think about solving this limit that involves the work we did up here with the tangent line. So remember, the whole talk in the last lesson about linear approximations was, again, in this picture or in the graph of a curve in general. Okay, if you only talk about a little bitty section of it and I draw a tangent line to it, if you're just concentrating on a small little section of the graph, the line and the curve will look a lot the same. And so as long as you are staying within a reasonable distance of where the tangent line was made, the curve function can be approximated pretty nicely by the line. Okay, and so I always think about in this limit, you really are studying the two functions when they're really close to x equals 1, which leads us to think maybe I could replace the two expressions with their linear approximations. We're going to do that on the next slide. So we're asked to find the limit approaching 1 of the natural log of x over x squared minus 3x plus 4. I think it was 4 or 1. Minus 4. Let's fix that real quick. It gave us the indeterminate form 0 over 0 when we just try and evaluate the limit as it is. But remember, the logarithm function just on its own has near the value x equals 1, at the value x equals 1, a tangent line that for values of x near 1 do a very good job to estimate it. We learned in the warm-up problem that the linear approximation of the numerator, when x is at 1, the linear approximation was just y equals x minus 1. And the linear approximation for the denominator function g of x was 5x minus 5. So what if we just maybe try and replace the two original expressions with the linear equations that approximate them near the value 1? So perhaps, let's give this a try. We're going to put in the equation of the tangent line to the logarithm function, which was x minus 1. And we're going to put in the equation of the tangent line to this other function at x equals 1, which was y equals 5x minus 5. So my question was, if you were to try the limit now, would you be able to solve it? And the answer is yes, because you can actually you can use a technique we've seen many times, and that is factoring and reducing. I just have to factor out this 5 again. And now, as long as x is only getting really close to 1, I can remove x minus 1 over x minus 1. And I see my limit would be 1/5. If you did pause the video a few minutes ago and try the original limit with your calculator, making a table, I hope you found that the limit was about 0.2, which is exactly the decimal value of 1/5. So in fact, this method of replacing the numerator with its linear approximation and the denominator with its linear approximation near 1 did actually produce the right answer. It turns out that'll always work. And that's what we know as L'Hopital's rule. Okay, so I want you to point out the significance of the 1 and the 5. Remember back to the first warm-up problem, the 1 really traces back to here, and 1 was the slope of this function's tangent line. And the 5 was the slope of this function's tangent line. And that is where we get this rule from. So here's what we know as L'Hopital's rule. The important stuff starts right here. It says if the limit of f of x over g of x when x approaches c produces the form 0 over 0, where we just saw that in the example, it says the limit can then be evaluated this way. Look at the derivatives of the two functions. In other words, the slopes of their tangent lines. And look at that and see if that limit exists. So in other words, here you'd be finding f prime of c divided by g prime of c. In other words, those are the slopes of the tangent lines to those functions at x equals c. And if that limit produces an answer, that's what the limit is. If this limit is still 0 over 0, we would cycle back around and apply the rule again. And you might have to go second derivative and second derivative until we get it. Okay, so either way, this is a nice way to solve a limit like that, is to, instead of looking at the original limit, if it's 0 over 0, differentiate the numerator, differentiate the denominator, try the limit again. Okay. This theorem has a bonus feature. Not only does it work when the limit is 0 over 0, but it also works if the limit is the form infinity divided by infinity. So you're going to see a couple instances today where you get a limit of that form, and maybe some of the techniques you've learned before today won't work for that, and you can use L'Hopital's rule for that as well. So let's take a look. We're just going to run through a couple of the examples now, and I'm going to focus on not only applying the rule, but also on differentiation, because you might need the chain rule, you might need the product rule or quotient rule as we go through these. The important first step in all of them is to verify that the limit you're working with is in the proper form. It must be 0 over 0 form or infinity over infinity form. If it's not one of those forms, you shouldn't be applying this rule. Okay, so in the first one, x is approaching 0. So if I try that in here, 2 times 0 is 0. E to the 0 is 1, and 1 minus 1 is 0. And of course, on the bottom, x is approaching 0. So we have the correct form. Now, what I'd like you to do in showing your work is not only to connect this with an equal sign and rewrite this using L'Hopital's rule, but it's a good thing right now to tell the person reading your work that you are actually going to use L'Hopital's rule. What I like to do is right on my equal sign, just put the first couple letters of his name. That way we know that now this next limit we're going to write is going to look different, but here's why it is different, because we're going to be now applying the differentiation to both of the parts. So the denominator's derivative is the derivative of x, which is 1. And in the numerator, we're finding the derivative of e to the 2x minus 1. Watch out for the chain rule. Okay, this is like e to the u. And the derivative of e to the u is e to the u times u prime. So this is going to be e to the 2x times 2. And then the derivative of the minus 1 is 0. We're not even going to write that. And we should try solving the limit now by plugging in the 0. So try it again. 2 times 0 is 0. E to the 0 is 1. And then 1 times 2 is 2. So this limit is equal to 2. Second problem, x is approaching 0, so the sine of 0 is 0, and x approaching 0. So this is the form 0 over 0. We will apply L'Hopital again. Take the derivative of the top and the bottom. The derivative of sine x is cosine x. The derivative of x is 1. So now we should try the limit again. Cosine of 0 is 1. So this limit is equal to 1. Now you might hopefully get an answer you recognize here. This is the exact limit I told you can memorize way back in August, except that back then we couldn't prove it this way because we hadn't learned derivatives yet. Okay, finally the last one. Let's apply L'Hopital's rule simply because I can tell it's 0 over 0. 4 times 0 is 0, so sine of 0 is 0. 3 times 0 is 0, and the sine of 0 is 0. Let's apply L'Hopital's rule again, and don't forget the chain rule. Your thought process is this is sine of u, and u is 4x, or u is 3x on the bottom. And so sine of u, the derivative is cosine of u times u prime. So the correct derivative is cosine 4x all times 4. I'm going to choose to write the 4 in the front here. And then for the sine of 3x, very similar. The derivative is going to be the cosine of 3x all times 3. I'm going to put the 3 in the front. Let's apply the limit now. If I plug in the 0, 4 times 0 is 0. The cosine of 0 is 1. So this is 4 times 1. Similarly, 3 times 0 is 0. Cosine 0 is 1. So this is 3 times 1. And my limit is 4/3. Very nice. So the last two are going to involve, or we're not going to see the answer directly right away. So we're going to talk about some other limit concepts that we've seen before as we go through the last couple steps of these. The first one, notice it's a limit to infinity, and so the denominator is just being x. It is going to become bigger and bigger. And the log of bigger and bigger numbers does get bigger and bigger also. So the initial form of this limit is infinity divided by infinity. So that is one of the forms we can use this rule for. So let's write our limit again by taking the derivatives of all the parts. So the derivative of x is 1, and the derivative of the natural log is 1 over x. Now, it's never a bad thing just to rewrite what you've got at this point. So if you know that the 1 on the bottom is not going to affect the answer at all, you can just go back and write the answer, write the limit as the limit of 1 over x, and you don't have to write the over 1 part. So now, though, we have the infinity. So we have to think about the concept 1 over infinity here. And what that's going to do. Well, this means we're going to start by doing things like 1 divided by 10, then 1 divided by 100, then 1 divided by 1,000. So the notion there is we go something like this. The fraction is going to be getting smaller and smaller because the denominator is getting bigger and bigger while the top is staying 1. So this is approaching the value 0. And that's our limit. So the notion here was, in the context of studying limits a while ago, we learned about the concept that if I get something that is a limit that is not 0 divided by something that is infinite, that always leads to a limit of 0. Something like if it's 5 over infinity, 7 over infinity, negative 2 over infinity, that is always a limit of 0. Okay. So this last one, though, it's a really good one. I've got an arc function here. Inverse. This is like inverse sine of x minus pi over 2 over x minus 1. X is approaching 1, but only from the left. Okay, let's first make sure this is indeterminate. Obviously, on the bottom, 1 minus 1 is 0. But the top, though, is, look carefully, the inverse sine of x, the inverse sine of 1 there, if you want to know that, that's the exact same question as asking you the sine of what number equals 1. And if you know your unit circle, the sine, one of them is the sine of pi over 2 equals 1, and that is actually what the correct inverse sine of 1 is. So the inverse sine of 1 is pi over 2, and so pi over 2 minus pi over 2 is 0, which means we can apply L'Hopital's rule. You may have to go and pull out your list of derivatives for this one because we don't differentiate the inverse sine functions very often. So if you want to go look it up and pause the video for a minute, you can. Otherwise, I'm going to keep filling it in. You will find that the derivative of the inverse sine function was 1 over the square root of 1 minus x squared. And since the derivative of x minus 1 is 1, I could write this all over 1, but I'm going to choose not to. I don't worry about that because it's not going to change the answer. So now let's look at this limit here. The numerator is going to stay a 1. But now let's look at the denominator. I'm going to get 1 squared, which is 1, and then 1 minus 1 is 0, and then the square root of 0 is 0. And now what do? I've got 1 over 0. This is a form we've seen before, though. I've got a limit that's in the form non-0 over 0. We remember from the past, that meant the limit is going to be infinite of some kind. Now, we don't know if it's positive or negative infinity, though, so this is where we're going to check that we're only coming from the left side. In fact, we can only come from the left side here because if the x in this limit was bigger than 1, then 1 minus x squared would be negative, and you couldn't even square root the negative number. So, in fact, we have to come from the left. So, to reason out if this limit is positive infinity or negative, let's look at some numbers super close to 1 but less than 1, like 0.9. So if I put that in here, 0.9 squared would be a decimal number that is still less than 1. And if I took 1 minus that, I'd get a tiny little positive number. Okay, so it might be like 1 minus 0.99. That would be a tiny positive number. And I square root that, it's still going to be a number super close to 0, but it's still all going to be positive. That allows me to put a little plus sign there like I used to do, which tells me that in this limit, the numerator is approaching 1, and the denominator is approaching a very, very tiny positive number. So at the end, I could reason out the answer by thinking about this as being like 1 divided by 0.00001, and that's going to give you a very large number and a very large positive number. So my conclusion here is this limit is infinite but positive. Okay, I hope this helps, and let me know. Please be in contact with me with any questions you might have about the assignment, and I look forward to seeing you in class again soon.